All right, everybody. Here's the second video about how natsets work. We'll be talking about operations in this one. Let's start out with the first predicate we defined, called member. And what it's going to do is it's going to look at a natset and a member. You give me a possible element of the natset, here necessarily a nat, and that natset, and I'll tell you up or down, is it in the set? How does it work? Well, you just walk down the list and see if you find it. Now you might have in the back of your head like, oh, why didn't he use exists_b or something? And I could have, but I figure I'd just write it recursively this way. Now, our invariant doesn't let us be fast or clever or anything here, right? All we know is that L won't have any duplicates. Uh, but, X could be at the front of the list. It could be the end of the list. We don't really know. Okay, this works. So you can see, okay, is it one a member of the empty net set? No. Is it a member of the evens to 10? No. Is 2? Yep. What about the other representation? Yep. And then let's look at natset yikes. So natset yikes was this 0, 1, 2, 2 list that is not meeting our invariant. Now it turns out that whether or not the invariant is met, member will always give us the right answer. That's actually a really nice property, right? This member function is just as well a predicate on whether or not something is an element of a list of nats. Great. Okay, you've got a couple exercises we want you to do here. So first, write a function is set-like, and it should return true when L is a good natset. That is to say, when it has no duplicates. There's a couple different ways to do this. Think about it. We've seen some related stuff from sorting. Maybe functions from there will be useful. My only advice there would be if you need a function from sorting that you defined yourself, be sure to copy it over into this file. Okay. Here's another operation, set insertion. So this is the first real operation we're going to have on these sets, not just a predicate. Now this isn't one of the ones we saw in the video. I said, okay, you need an intersection or the classical math operations, and then insertion is just sort of a degenerate form of union. Now here, insertion is such an important computational operation that we're going to define it custom ourselves, and we'll actually define union in terms of this one. Okay, so here's the whole definition. How do we put something into the set? Well, we ask, hey, is it already in there? If so, just return the set we've been given, L. We don't have to do anything, right? We're already good to go. If it isn't already in there, okay, cons it onto the front, and now we're good to go. So I want you to verify for yourself, just in your mind, if L is a valid natset, if it passes as set-like, if there's no duplicates, will that still be true on the other end of this function? Does set insert preserve the invariant? So relatedly, here's a little short quiz. What does set insert assume about its input? Will its output always be set-like? If yes, why? If not, give an example of a case where its output is set-like and a case where its output isn't set-like. Pause the video and think about it. Okay. So you might think, well, this will always be good. The answer will always be set-like because we'll never duplicate anything. And that's a good intuition, but it's missing a key fact. If L starts out set-like, it'll stay set-like. We'll keep the invariant. But what if L was natset yikes? Okay, what about set insert 3 natset yikes? Ah, we don't have the invariant because we didn't come in with the invariant, and in set insert isn't doing anything to sort of say like, well, maybe make sure I remove all the other duplicates or anything like that. So you might think that it doesn't matter, but for set insert's result to have the invariant, it needs to already have the invariant. Now, on the a plus side is it's not going to make things worse, right? If we insert 2 into natset yikes, we don't get an extra 2 at the front. The member check was good enough not to insert an extra one, but nothing happens to get rid of the doubles. You might be able to imagine a version of this function where we change it to sort of enforce the invariant and remove the duplicates from L, but I'm not certain that's really a win, right? What that'll mean is that we'll always be checking for all these duplicates, and that'll be slower, right? It'll be all this extra work we're doing just to make sure things are coherent. So instead we'll say, look, set insert will take good natsets to good natsets, but if you give it a bad list, a list that isn't really, a set, doesn't have the set property, then all bets are off. Okay. So here's how we use set insert to define union. Contrast this with the list function append. It's pretty similar to append. It's almost identical. Rather than using cons, though, we're using set insert to make sure when we come across an X from L1, we never bother if there are duplicates in the recursive bit of the union. You could have defined this function differently. Here we're doing recursion on L1. That's the subject of our loop, our recursion. But we could have just as easily done it on L2. I just happen to like choosing the first argument. I think it's kind of a standard convention. Okay, so here's a little quiz for you to sort of practice for yourself. Define a set L such that the numbers 0 through 10 are all in union L evens to 10. What is L? What concrete list representation will union L evens to 10 have for your L? Pause the video. So you have a lot of options here. A lot of different things could be in the union. Let's recall what evens to 10 was. So we want to get out a set that's 0 through 10. Now, it won't necessarily be in order. In fact, union's only going to put things at the front because it uses set insert, which only puts things at the front. But we need to put in some missing elements. 1, 3, 5, 7, 9. So one answer could be this. Right? Another answer could be this. Right? Order doesn't really matter. Now, these will have different concrete representations. Here, let me do it as a pair so you can see both of them at once. So these represent the same set, but they're a little bit different. Make that a little bigger for you. Okay, let's do one more. You maybe you're feeling like a little cheeky, a little frisky, and you're like, oh, I got an idea here. Let me show you something. Boop. What? Uh-oh. What? What? Is that gonna even work? Let's check. It is. And in fact, you'll notice the tail remains the same. Union is defined in terms of set insert. So if it's already in the set, it doesn't hurt to have it in there when you're doing the union, right? I could have added a bunch of other stuff. Another question. What are the requirements on union? Does L1 have to be set like? Does L2 have to be set like? So a thing you can run on your own. I'm not going to give you the answer, but you can figure it out. L. So let's do 1, 3, 5, 7, 9, 2, 2, 2. And I just want you to think, what is this going to be? I'll show you that it's well typed. It's a natset. Will it have the set property? Think about it for yourself. If you're not sure, ask on Zulab, but I think just running the compute will give you the answer. And then I want you to figure out why is that the answer. Okay, so after that, I want you to define the intersection operation. That's going to look a lot like union, but you're going to have to sort of do a different thing, right? So we want to compute the things that are in both. So some stuff we've already defined will be helpful there. I'd like you to implement subset. Let me know when L1 is a subset of L2. I think I've shown you this notation before. Here, I think we saw it early on. Here, I'm just taking both my arguments of the same type in one parenthesis. No real difference there. So then I want you to define subset. And then lastly, I want you to give me a function that determines when two sets are equal. Now, as we've seen, their concrete representations may not be equal, but if they represent the same set, this function should be true. So in particular, my L and my L prime, right? These are equal sets, even though the lists are not identical, right? So again, we're having to do sort of that distinction between like, well, these are different representations of sets, but they represent the same set, just in different orders. So set equal should return true for these, but neither of those should be equal to this one, which has extra elements 2 and 4 and 10. Okay, so you'll define those. After that, we've given you some unit tests here. After that, we'll look at a different representation for how to work with sets as lists. Okay, thanks, y'all.